Hey everyone, Mr. Montgomery again. Today we are on lesson 5 of wave properties, and today we are really going to be diving into seismic waves. So, the main lesson objective today is, of course, to be able to tell about seismic waves, but also to be able to calculate wave speed, frequency, and wavelength. So there's going to be a little bit of math, but not a ton. So, there are other types of waves called seismic waves. These are vibrations that are carried throughout the Earth, and this is stuff that we can actually feel from the ground. So this is going to be due to largely because of plate tectonic movements and like stuff like volcanic eruptions and stuff like that. These super large disturbances that take place on Earth all the time. Well, maybe not all the time, but pretty often. If you guys watch any form of the news, whether it's on social media or regular TV, you guys know that places like California have earthquakes all the time, which causes stuff like mudslides and landslides and buildings collapsing and all horrific stuff. So earthquakes, or I'm sorry, seismic waves, which are typically viewed as earthquakes. The really crazy part about it is there's no way for us to actually detect these occurrences before they happen. We have early warning systems for stuff like we're getting better with tornadoes. We are pretty good with hurricanes and tropical storms and all this other stuff. But when it comes to seismic waves, we can put equipment into the ground to detect the rate or size of the waves themselves, but unfortunately, there's no like early warning system that there's going to be these large seismic wave disturbances occurring, and when or where it's going to occur either. So there's 3 types of seismic waves that we are going to be talking about. First are P waves. Next we have S waves, and then lastly we have surface waves. So when it comes to P waves, these waves in particular move by using longitudinal wave movement, that back and forth motion, if you recall back from like lesson 1 or 2, with the slinky being pushed across the table, and you see that compression move through the slinky, reflect off the end, and bounce back. So those are longitudinal waves. It just pushes straight through, straight forward in that back and forth type motion. But also, the really cool thing about P waves is that they are the absolute fastest. They are going to be the first thing that you feel when there's seismic wave activity. And next we have S waves, or also known as secondary waves. So for P waves, they're called primary also, right? So P waves, primary waves, because they're first, right? And S waves, since they're second, we're going to call them secondary waves also. These actually move in transverse wave movements, which cause the ground to shake up and down. So the P waves will cause the ground to shift back and forth, and you'll feel that like unstable, wobbly motion. But the S waves, that will make you feel like you're kind of bouncing off the ground, which is pretty crazy to think of. I mean, just imagine for a moment that you're standing on the street or sidewalk, whatever, you're outside doing something, and out of nowhere, you start feeling this back and forth shifting. And then out of nowhere again, moments later, you feel this crazy vibrations bumping up and down. It makes you feel like you're jumping without even jumping. And then lastly, we have surface waves, which are the absolute slowest. These are going to be the last kinds of seismic waves that are traveling or to reach any sort of location. And a lot of this is because they stick strictly to the surface of the Earth. They do not go through the Earth's mantle and outer core and inner core like other waves do. So one thing I almost forgot to mention to you guys with P waves. Here's the really cool thing about P waves. They can move through liquids and solids. So no matter what the density is, they still move through those mediums. But when it comes to S waves, they cannot move through that solid part of the core and these different densities that are found close to the center of the Earth. They can move through the mantle, but you see where these dotted lines are? That's the extent of it. It can't go past or through the outer core or inner core of the Earth. So this whole area here is what's commonly called the shadow zone. So they won't really notice any disturbances, but these other locations will feel disturbances. Now for P waves, here's what gets really cool and crazy. It can move straight through this core. Now it will refract to a degree. So you can see like these red lines kind of going in. It hits this different medium, this different density. It diffracts. You see it kind of like bubble out a little bit. And then once it hits the end of that outer core, it diffracts again and just kind of shoots straight down. Just like when we took the laser and we were shooting a prism with it in the classroom, and you see the laser shoot off in multiple different directions. Similar idea. These waves also refract, but it's just with a different type of medium. Now, the shadow zones for P waves are much smaller. You'll notice that there's this little gap between these red dotted lines and these black dotted lines. This little space is the only place I won't feel any disturbances. Or if they do, it's going to be insanely small where they probably wouldn't notice it. And same thing on the opposite side as well. So smaller shadow zones for P waves, much larger shadow zones for S waves. Now let's check in real quick before we go into the math portion. Which type of seismic waves move using longitudinal waves? Is it surface waves, S waves, or P waves? And I know you can't click, so just either point to the answer on the screen or just kind of really hyper focus on that one word or phrase that's on the screen. And I'm hoping you're all really focusing on P waves. P waves are the fastest, and they move using longitudinal waves. Okay, so now comes the math portion of the lesson. So we're going to be talking about some different variables and formulas to help us figure out the speed, frequency, and wavelength of waves. Now, personally, I'm not going to really grill you guys over these different variables that are put into the formulas because I know they can get confusing, especially this little sucker down here called lambda. Super weird and goofy looking. But if you're not in my class, then you may want to take that part a little bit more seriously just in case your teacher does quiz you on it. Now for speed, the variable is going to be v. For frequency, it's going to be a lowercase f. And wavelength, we use this symbol called lambda, which is like this weird upside down y that's like backwards. Super weird. One other way you could try writing it is just kind of like writing like a very sharp capital A without the line going across, and then give it a little tail down here, and then like a little weird hat at the top or something. Okay, and now here are the three formulas we're really going to focus on. To calculate speed, all you got to do is take the frequency, which is always going to be measured in hertz, and multiply that by the wavelength. And yes, this little star thing just means multiplication. If you are copying this down, you can just put these words in parentheses if that's easier for you to remember and understand. Either way is correct. Now, for frequency, we have to take the speed, which is usually going to be a distance, whether it's centimeters or meters, per second. It's always going to be in seconds, okay? And we divide that by the wavelength, which is a measure of distance, which, for me, I'm not going to go nuts into like stuff like nanometers, which would be gamma rays. That would be super, super crazy. We're going to primarily stick with centimeters or meters, and you will be able to tell which one we are dealing with for that problem, because they will mention in the problem centimeters per second or meters per second, or if they are just telling you what the wavelength is, so that way you can calculate frequency, it'll tell you 20 meters or 2 centimeters. It will definitely tell you the unit of measure for that particular problem. So you have to pay very close attention. And then lastly, to calculate wavelength, we need to take the speed and divide that by the frequency. Now for our units of measure for each category here, for speed, like I just mentioned, it's always going to be in seconds. It's not going to be in minutes, hours, days, or years. None of that. Seconds only. waves move very, very fast, especially when we start going into light waves and sound waves and all that kind of fun stuff that we're going to be diving into in the next few units. And for wavelength, like I just mentioned, centimeters or meters, it will tell you in the problem itself. And then lastly, for frequency, we use a unit measure called hertz. So if you're given the answer for a calculated frequency, you must put hertz or the abbreviation Hz. Now this is just a walkthrough problem that I created for you guys to visually see and understand better how the formula operates. And some of you might be thinking, I know, it's super easy, it's just multiplication, I get it. And I get it. So I'm not going to waste too much time on this. So here is the word problem. I almost said story problem because I have a first grade brain still. So a wave has a frequency of 90 hertz, Hz, hertz, and a wavelength of 20 meters. What is the speed of the wave? Well, first you have to figure out what formula. For this, it's going to be speed equals frequency times wavelength. And then next we just take those two numbers and plug them into the right spot. So wavelength is 20 meters because it's distance. So we would plug that in right there. And the frequency is 90 hertz. And we know it's frequency because it has Hz, which is the abbreviation for hertz. And you would just plug that in right there, which gives you 90 times 20. And 90 times 20 gives you 1800. But it's not just 1800, it's 1800 meters per second. And we know it needs to be meters per second instead of centimeters because right here in the problem, it says meters. It has that abbreviation for meters right there, 20 20 meters. Now for the frequency equation, same idea. Read the problem first, figure out what formula you need afterwards. A wave is traveling at 300 meters per second. So whenever you see that slash, it's always going to mean per. So 300 meters per second that this wave is traveling. So every single second, you have 300 waves passing a certain point. And it has a wavelength of 20 meters. What is the frequency of the wave? Well, we know that we need the frequency formula because it's telling us we need it. So frequency equals speed times wavelength. So which one is which? Well, the speed is going to have the unit of measure with the time, meters per second right there. So 300 gets popped in right there. For the wavelength, it's distance only. So which would be 20 because there's only a unit of measure of distance right there. So 300 divided by 20, which would give us 15 hertz as our frequency. That's it. All right, nothing super crazy. A lot of these, you can probably do some mental math unless it gets really, really crazy. The next one gets a little crazy. You'd probably have to use a calculator for. But for anyone that is in my classroom, I will not give you anything super hard like what's on the next one. Now for our last formula, which is wavelength. A wave with a frequency of 500 hertz is traveling at 200 meters per second. What is the wavelength of the wave? So we know our formula already, right? Wavelength equals speed divided by frequency. And we just take those numbers and plug them in. So which one's our speed? Well, it's 200 because it gives us the distance and time. So 200. And then our frequency, which is 500 because it has the abbreviation for hertz right there. So we know it's got to get plugged in there. So 200 divided by 500 would give us 0.4. But there's no unit of measure. What should the unit of measure be for this particular answer? Well, if it's wavelength, we know it has to be distance. So what abbreviation for distance would make the most sense? Look at this number real quick. And look at this number real quick. There's a special letter hidden in there for you to figure out. Now, should we put hertz? No, because hertz isn't a measure of wavelength of distance, that's the frequency. So what about seconds? Well, that's just time. That doesn't really make sense either. But meters make sense. Wavelength is a measure of distance, and so is meters. So this would be 0.4 meters. And that's it. All right, so I'm really hoping that this video either helped you catch up with any lessons that you missed, or maybe just helped refresh your memory on the subject topic, or maybe even helped you understand it better. But if you have any questions, please feel free to ask at any time. Or if you're not in my classroom and you just stumbled upon this, please make sure you ask your teacher if you have any questions. But as always, guys, I hope you have a great day, and I'll see you next video.